Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology under the LG University. Now in our today's session we are going to discuss about the kind of asynchronous sequential circuit hazards where how the different kind of critical or non-critical conditions kind of drawbacks arises during the design of this asynchronous sequential circuits. Based on that, when designing asynchronous circuits, it can happen that you get spikes like the glitches from 0 to 1, 1 to 0 on the signals values, cause some unwanted transitions in the output before shutting down the stable state. So we always want a kind of stable state needs to be designed. Let's say one state is 0 0, the another one is 0 1, another the third one is a 1 0, and fourth one is 1 1. So instead of this all these stable states, we may get a kind of unstable state like 0 0 that directly going into a 1 1. Maybe 0 0 is going into a 1 0 and it will again go to 1 1. So all those kind of glitches are required or maybe may occur in a circuit because of some kind of hazards in designing of those kind of asynchronous sequential circuits. So two types of hazard are there. One is the logic hazard, another one is a function hazards, right? So caused by the logic is caused by non-instantaneous changes in a circuit signals, and the functional again inherently based on the designing criteria. So can result in erroneous behavior. The glitches when fed to some other circuit may result in incorrect behavior. So this due to the presence of several signaling paths which have we have different delay times, right? So based on that, if we further see a kind of various types of hazard like static 1, it goes to 1, static 0 to 0, dynamic 1 to 0, and dynamic 0 to 1, right? So this is kind of glitches where dynamic and static glitches are always there. So this we consider from static 1 to 1, that means this line goes straight like 1 remains 1, but in between see you will see the one glitch, that is the 0 glitch. Same way is a 0. See, one glitch is required. I mean, the one glitch is coming in between, and that is defined as a 1. So this kind of static behavior you can see in this kind of hazards. Same in a dynamically, that means more number of 1 and 0 changes in a circuit diagram or in a timing diagram. So based on that, if we hazard may occur in the circuit below if the transition is x3, x2, and x1 is from 111 to 110, right? This is only because of the kind of delay, and you can see further this term like x1 is given like that way, so p is going like that way, q is going like that way, and finally the f is the kind of hazard in between. This kind of delay is going to be coming in a kind of asynchronous sequential circuit, and based on that, see this f goes to 0. So this is a one kind of unwanted transition from 1 to 0, and this is a one kind of static hazard. Like same way, in some of the free circuits you will see this how you can remove this kind of hazards by just introducing one AND gate in this particular asynchronous sequential circuit, and based on that you can see the previous circuit where the kind of K map, see this is the one kind of, see 1 1 is available here, 1 1 is also available here, we'll make one more group here. By that way, so delay can be maintained in this our next hazard. Like see this band is there, and based on that we'll add one more AND gate, and based on that you see the output is coming flat, right? So there is no glitches in between. We just introduce one more boolean function inside, and we can remove this kind of hazard. Now this is a one kind of design criteria, and you need to identify in real case once you physically implement this kind of digital circuit on a trainer board, right? So this kind of terminology you have to understand, you have to learn about those kind of designing criteria and process how to avoid this kind of static hazard, like a possibility to remove this kind of static hazard. Like here static hazard is created if two adjacent ones are not covered by their own products in a SOP. That's what we have just, it's like we have taken two groups, right, and two groups are separately we are taking. That means our main goal is to reduce the number of gates, but we are not taking care of a kind of unwanted delays, right? Thus one can remove the risk of static hazard by adding implicants so that all adjacent ones are covered with their own circles. If you have POS implementation, you have to ensure that all adjacent zeros are covered by the separate product term, right? So ultimately here we are going to add this two ones. And so initially our assumption is that this is a one of the group that is covered two zeros. This is two second group that is also covered two zeros. So we have to incorporate the two zeros by making a complete group, and by that we introducing, see here, making a delay, and based on that, I mean, you are managing the delay, and by that way, see, you can avoid this kind of static hazards. Now dynamic hazards, again, the dynamic hazard causes a several spikes at the output, and the dynamic hazard is caused by the circuit structure. So you can see the kind of example of this dynamic hazards where repeatedly 1 and 0 is going to be transit in a one timing diagram. The example of this dynamic hazard is like the following equation produces no hazard if you implement it and or on structure, but if we implement this equation with the following multi-level logic, dynamic hazard will come, right? So here you can see a kind of f is equal to this, you can have this kind of and or, so this we can consider as a level 1 and this will consider as a level 2. Based on that we draw the kind of timing diagram, and you will have a 1 gate delay, right? So here it will get the 1 get delay. So immediately see this x4, if you are directly going to apply to f, see that will create a problem. So instead of that, we'll generate a kind of delay in between putting this kind of AND gate, and like that way. So here there is a delay, here we will get in directly this is level number 1 and level number 2. So how we can design this x1, x2, x3 and x4, we have given a kind of the step manner. So this is the first level 1, level 2, level 3, and this particular level 4. So now level 4 depends on the x1, x2, x3, x4 with the certain time duration. Based on that, if we managing this particular time duration, see, certainly we can avoid this kind of dynamic hazards from the structure, from the design. So a dynamic hazard, so that can be avoided by using the two-level logic. Then during minimization, we must ensure that the circuit is free from static hazard, then there is no dynamic hazard as well. So glitches in asynchronous circuit, like we can get the output spike in an asynchronous sequential circuit when one stable state is switching to another one by means of passing through several unstable states. So this phenomenon is not a hazard, but you can see this. This is C00, that passing through 1 0, right? But this 0 0 again it will come to 1 0, right? So which is passing through some of the stable states, and then that way you can have a kind of glitches in between the operations, right? So this is one of the example is given. Race condition, so here this particular race condition is nothing but exists in asynchronous sequential circuits when two or more binary states variables change value in response to the change in a input variable. So here I can explain like you, there are, let's say, 3 stages. So the third stage input depends on the output of second stage. The second stage input depends on the output of first stage. But here during the operation, let's say the third stage will take the input directly from the output of first stage, so it's omitting the second stage or bypassing the second stage. This condition we can refer as a race round condition or race condition, right? So when unequal delays, this is nothing but a kind of delays, right? So that the game of time lapses between one state to another stage or one level to another level, right? So when unequal delays are encountered, a race condition may cause the state variable to change the unpredictable manner. So based on that, if we define a kind of race conditions occur when two or more state variables are supposed to change simultaneously, right? So here we are taking 3 stages, and we just discuss about the example where due to the change in input, so from 0 0, see, it will should go to 0 1, then it will go to 1 1 or maybe 0 1, like this is the sequence. So in some of the transition you can see the kind of possible transition is from 0 0 to 1 1, or 0 0 to 0 1 to 1 1, or 0 0 to 1 0 to 1 1. See, this kind of term where output you can observe is 1 1 1 1 1 1 for both the 3 conditions. So ultimately when this goes to the actual output, so this kind of races are not non-critical races, right? So there is no criticality inside, because the output remains the same of any sequence it would follow. Again for this one, you can see the possible transition is from 0 0 to either it goes to 1 1 and then will give you the output of 0 1 directly with the 0 1, or from 0 0 to 1 0 to 1 1 to 0 1, that is also possible. So this kind of race conditions are like the non-critical race conditions because output remains the same. So here the critical versus non-critical race conditions, where you can define a kind of non-critical or kind of critical races. So here you can see the part of the critical races, the outputs is completely going to be changed. So 0 0 directly goes the output to 1 1, 0 0 to 0 1, and 0 0 to 1 0. See, the output is continuously changing, so that is not a same output. That's why this condition is a critical condition, because anyway here the state or output states are completely changed in this behavior, right? Same way, one more example you can see for the critical races, where the three possible transitions, instead of this, say it will follow this kind of terminology, right? So if different transitions lead to a different final states, then it is a critical condition. So for non-critical race condition, output remains the same, even your input follows the different kind of states, but final state would be the same as your actual output. But in a critical conditions, see, output is completely changed, right? So you need to understand this particular race condition. This is a kind of state way. Same way, non-critical condition, we have just explained, the output remains the same for both the cases. So you can see here case number 1 and case number 2. So output remains the same, even your input follows or gone through a different states like 0 0 1 0 1 1 and 0 1. See, the first case the output is 1 1 1 1 and 1 1, even it will come with the kind of through a middle level some states. Here the output remains the same as per the actual output. That's why this condition of race is defined as a non-critical conditions, right? Again, based on that is some of the issues of oscillations. You can see what is this kind of oscillations, where oscillations is like continuously you are getting the output is like 0 1 0 1 0 1. It is a kind of pulse train of 0 1 0 1 0 1. So in asynchronous sequential circuit may become unstable and oscillate between the unstable states because of the presence of the feedback, of course. So the instability conditions can be detected from the transition table. So consider the following circuit, where if you draw the kind of transition table of this particular circuit, because here the output is again feeding back to small y in form of this going to this NAND gate, and you will see a kind of oscillation states in between. Oscillations is like it's never come into a kind of stable states. So more or less these conditions we always define as a unstable state. So this excitation table, if you draw with this function of y is equal to x1 dash into x2 plus x2 into y dash, based on that if you draw a kind of transition table, you will realize a kind of oscillations issue, right? So issues due to the oscillations, like this is what y, x1 and x2. So this is 0 1 and 0, like this one. This kind of oscillations is going like 0 1 0, again it will come to 1 0, right? So here the transition table you can see in this particular table, in this particular slide, like those values of y that are equal to y are circled and represent the stable states, right? Because this 0 correspond to 0, this 1 correspond to 1, but this one here is, this is what the transition is, right? So this is 1 and 0. You can see here the transition, because this 0 is having the condition of 0, this 0 having the condition of 0, this is a stable state. This 1 is having the condition of 1 here, this is also a stable state. But instead of that, see, this 0, this 1, this 1, this 0 and this 1 will have a kind of unstable conditions, right? This is only because of the transitions. So those values of y that are same equal to a small y circled and they represent the stable state. But when the input is x1 and x2 is 1 1 1 1, see, the state variable alternates between 0 and 1 indefinitely. So that's what this particular terminology, where x1 and x2 is equal to 1 1, so it will oscillate into this unstable conditions, right? So this is more or less with the learning about the different hazards that may come across while designing of asynchronous sequential circuits, right? Thank you, dear students. If you have any doubt, please write in the comment box. Thank you very much.